Okay, so here we're going to talk about section 1.6. Honestly, there isn't a whole lot new in 1.6. Well, really, there isn't anything new, at least in terms of the math. But basically, 1.6 is applications, right? The word problems applying all this stuff that we've done so far. Okay. Um, there's a couple different types of problems, but one of the types here is this. It's like an economy, okay, and it's just seeing how the different sectors relate to each other. Okay, so let's check this out. So let's suppose an economy has four sectors. There's the agriculture, laziness, let's just call it A. The energy sector has got E for E, manufacturing is M, and transportation is T. And basically, the point is they all interact with each other, right? They buy and sell each other's goods. Okay. The bigger point here is we want everything to balance, right? Everybody's input and everybody's output has to basically balance, or they have to be equal, right? Otherwise, you'd have chaos. Okay. So it's telling me here, I mean, we can go back through, but basically sector A, he sells 10% to E, 25 to M, and retains the rest. Sector E does its thing, blah, 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 blah. Right. And we can go back one through one, but let me make sure what this chart is talking about. You want to construct the exchange table. Okay. So what these are talking about here, these are the outputs for each one, and you're going to put that in the corresponding who was it purchased by, right? So these would be the outputs of the agriculture, these are the outputs of the energy, these are the manufacturing outputs, these are the transportation. And purchased by, these would be kind of like the inputs, right? So the agriculture is going to input, basically retain itself, its own thing. Um, and then it would input the energy, input something from the manufacturing, and import something from the transportation. Then it'll be the same for the energy, manufacturing, transportation, blah blah blah. Okay, so let's fill in this chart for starters. Okay, so we can go back and nitty gritty this more. All right, so sector A, so the agriculture sells 10% of its output to E, right? So the output of the agriculture, 10% is going to the energy, right? So that's this stuff here, right? Then 25% to M, right? So 25% to the manufacturing, oh, I'm sorry, I just did it. But 10%, right? You got to, it's a percentage. You got to move the decimal over. So it's really 0.10, right? And then 25%, well, move the decimal over because it's a percentage. But then it retains the rest. Okay. So what does that mean? That means the agriculture is not selling, or basically transportation is not buying anything from the agricultural. So that would be zero. Okay. But if agriculture retains the rest, that means 10% of it is going to energy, 25% is going to manufacturing. That's only 35. So that means 65% of its stuff it's keeping, right? Or it's purchased by, sure, but I mean it's more like it's keeping it. You'll see. Then you do the same with the energy one, right? So the energy sells 30% to A, or 0.30 if you want to think it that way. Uh 35% to M, so that would be 0.35, and 25% to the transportation. And then it retains the rest. Okay. So there's 30, 60, 80, 90. So that means it would keep 10%, right? Or the output, 10% of its output is it's keeping for the energy. Kind of also you can kind of see this go. It almost lends itself perfectly to a matrix already, right? And also you can kind of see the stuff on the diagonal, right? See agriculture to agriculture, energy to energy, manufacturing to manufacturing, transportation to transportation. So that diagonal is definitely going to be the stuff that people retain. Okay. But anyway, so then manufacturing. All right. So M 30% goes to A, 15 to E, right? It's going to retain some, but then it gets 40% to T. All right. So what do we got? 40, 70, 85. So that means 15% it would maintain. Okay. Then the transportation, 20% goes to A, 10% goes to E, 30% goes to M, and it retains the rest. So there's your 30, 30, 60. So it's going to maintain 40. All right. Now, the point here is now we can set up the equation, right? Or we want to find a set of equilibrium prices. So we want prices for this, right? So agriculture is going to sell its stuff, right? Energy is going to sell its stuff. Manufacturing is going to sell its stuff. And transportation is going to sell its stuff. Okay. But the whole point is it's got a balance, right? So the stuff that agriculture, I mean, looking at it from agriculture's point of view, right? 65% of the price, right? 30% of the price of energy, 30% of the price of manufacturing, 30% or 20% of the transportation, but that should equal whatever the price of the agriculture is, right? Because it's paying out, right? It's paying out this, but it's coming from here, 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 and here. The energy is coming from here, 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 and here. Manufacturing is coming from here, here, and so forth and so on, right? So you can use X1, X2, whatever you want. But like this book, and it's pretty common. What they're going to do is they're going to use this P for price, but they're going to think of it as P sub A, then P sub E, then P sub M, then P sub T, right? So P for price, but they're using the subscripts A, E, M, and T so that you can see which one it is. Okay. So basically, the equations here are 65% or 0.65 of whatever the price of the agriculture plus 0.30 of whatever the price for the energy plus 30% of whatever the price of the manufacturing plus 20% of whatever the price for the transportation is. That's the outputs here, right? But that's what agriculture is buying, right? Or that's how much it would be paying. Okay. So that means P of A would have to equal all of this, right? That way, all of its stuff that it's buying, it's basically, it's keeping this shirt, right? But it's got to buy this, it's got to buy this, it's got to buy this. So that way, all your inputs and your outputs balance. Then you do the same thing for the next one, right? So it's the same 0.10 of the price of A plus 0.10 of the price of E plus 0.15 price of M plus 0.10 price of T would have to be your price of the energy. And then the same thing with the next row. So 0.25 P of A plus 0.35 P of E plus 0.15 P of M plus 0.30 P of T would have to be equal to your price of the manufacturing. And the same with the last one. I'm going to just write it, right? But it's really 0 P of A plus 0.25 P of E plus 0.40 P of M plus 0.40 P of T would have to equal your P of T. All right, so there's your system of equations that we need to solve, okay? But here's the thing. You could set it up like this, but your variables are on both sides, right? So just like a normal system, I want the variables on one side and I need my constant to be on the other. But the whole idea here is this P of A has to go over here with this P of A. This P of E would have to go over here. This P of M would have to go over here. This P of T would have to go over here. But in order to do that, you would subtract off one of them, 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 right? So really, it's going to be 0.65 minus 1 here, which is basically, well, okay. Well, we just jump to this, see where this is going to go. So like basically, when you go to set up your matrix here, your column 1 is going to be your P of A, column 2 is P of E, P of M, P of T. But then when you move everything over here, this is going to be a bunch of zeros. So that's going to turn it into basically a homogeneous system, right? Because all my variables would end up coming together and there would be no actual constant here. If we want everything to balance, it all balances out to zero, right? That's why it's a homogeneous, right? But the point is, if I move this over, this is going to end up being a negative 0.35. Then this would be the 0.3, 0.3, 0.2, and then augmenting it with zero. Then this would be 0.1. Then when I subtract 1 here, this is going to be a negative 0.9, right? Then you got the 0.15, 0.1. And then when I move that over, this is now going to be 0. And then same thing here. This is going to be 0.25, 0.35. Subtract 1 is now going to be a negative 0.85. And then 0.3, move it over to 0. Then you're going to have 0, 0.25, 0.4, and then when I subtract it, you're going to have a negative 0.60. All right, so there's my corresponding system as an augmented matrix, okay? Move all the variables over. I mean, if you really thought about it, you could have jumped right to this because think of it as what is the agriculture doing? It's spending this, but it's not spending this, right? To make everything balance. You could think of the energy, it's spending these, it's not spending this to balance, right? It's spending this, not spending this to balance, spending this to not spend this to balance, right? So you could have just jumped to it if you thought of it like that. But anyway, you do that by hand, but that's some crazy numbers here. You're more than welcome, please use a calculator, right? So this is what, a 4x5. Well, here, actually, hopefully we've done this enough. You guys know what I'm doing. right? But 0.45, you're just doing the negative 0.35, right? 0.3, 0.3, 0.20, 0.1, negative 0.9, 0.15, 1, 0, 0.35, negative 0.85, 0.3, 0, 0, 0.25, 0.4, negative 0.6, and 0. All right, so let's make sure. All right. So we got negative 0.35, 0.1, 0.25, 0.3, negative 0.9, 0.35, 0.25, 0.3, 0.15, 0.85, 0.2, 0.1, 0.30, and then the 0 here. Now, also that 0, 1, that vector, you didn't really have to type those in, right? That was the whole point of the last section, right? It's never going to change, right? It's always going to be a bunch of zeros. Okay. Also, the math behind this, let's think about this. What is the answer going to be here? Well, since this is a homogeneous system, that means this will always have a solution. It's either going to be the trivial one or it's going to have infinitely many of them. Well, hopefully it's not only the trivial one, because that means everything's free, right? And that doesn't make sense. Because I mean, if that were the case, if this turned out to be all pivot columns, then everybody would be zero. That means all my prices are free. Technically would solve the system, but man, that would be in a boring economy. That means nothing is happening. Okay. So what does that mean? There's got to be an infinite number of ways. There's got to be an infinite number of prices that would make this work, right? But there's a dependency there. That's the question. What are we depending on? Okay. So if we reduce row echelon form that matrix, we get this. Woo, it's crazy. You could turn it into a fraction here, right? Well, let me just write this. Okay. So we got 100,010,000,100,000. Okay. Then here, this is negative 728. Whoa, over 359. Then negative 572 over 1077. Oh, I see what's going on. And then negative 1258 divided by 1077. But here's the thing, right? Well, okay, you hopefully you're already telling me. You might, in general, could this have no solution? Yes, you would determine that by going over here and seeing if there's a number here. But this particular problem can't have that because this is a homogeneous system. So this is guaranteed to be a zero. So this is guaranteed to have a solution. And this is good because now we actually have an economy because we had a pivot, a non-pivot column. Non-pivot column, we got a free variable. Okay. But where is the free variable? The free variable is in the 1, 2, 3, fourth column. So manufacturing is the one that matters, basically. Everybody's depending on manufacturing. If I know manufacturing's price, you know everybody's price, right? Technically, if you know one, you know everybody's. But the way this was set up like this, manufacturing is the key. Okay. So what is the solution? Your price vector with all of them, okay, is basically a scalar multiple of P sub m, right? Where P sub m would be the first one that, remember, this is the agricultural price minus this equals zero. So you move it over. So it's really 728 divided by 359. The same thing, this would be 572 divided by the 1077. 1070. Oh my God, 1077. And then the 125 divided by 1077. But wait a minute, that the last one there is your manufacturing there, so that's your one, right? Okay. So the point here is your manufacturing is itself, and then this one is 125th or 125 over 1077 of whatever that is. Okay, so this would describe the whole thing, right? Just to give you an example, right? If what I'm saying here is if manufacturing was $1, then well, actually it was from here. You do it from here. So if manufacturing was $1, then this one would be $1.17 roughly. This one would be roughly 53 cents. This one would be $2.03, right? Or if you check these out, the crazy numbers here, but they're just nice multiples of these here, right? So I mean, like if you could, then maybe pick 1077, right? If well, you're not picking, but I'm saying if manufacturing was 1077, this would be 125. This would be 572. If manufacturing is 1077, then this one would be 2184, if you follow what I did there. But anyway, the point is you can see how the different sectors relate to each other. If I know one, you really know the rest. Okay. All right. So that's one type of example. And there's all kinds of things you could do with these. But another one, you guys have sort of seen these chemical equations before, right? So if you've seen anything in chemistry, so basically what's happening here, if you've never seen this before, I would imagine you've probably seen at least some of this, maybe. But these different letters are representing different elements, right? So the capital letter by itself, or a capital letter with a small, it's just laziness. That's what they give it. So Na is referring to one different thing, right? P is one element, O is one element, Ba is one element, N is one element, O is one element, right? O is for oxygen, nitrogen, barium, oxygen. P, I believe, is phosphorus. I believe. I don't remember. I think it's, oh yeah, phosphorus. And then A is sodium, right? Okay. So the way these things work, it works very similar to math. It's just that chemistry uses their own notation. Okay. So first of all, what is this saying? This is one molecule, right? And we're going to add another molecule. And when you do that, usually when you heat it or something like that, it turns it into something else. So it splits it into different ways. And this molecule plus some other type of molecule. Or the word here is when solutions of sodium phosphate and barium nitrate are mixed, the result is barium phosphate and sodium nitrate. Those are just the fancy names for them, right? But that's the chemical reaction that occurs here. Okay. Kind of what you want to do is you want to think of it as kind of like these are exponents, right? But this chemical here has 3 sodiums, 1 phosphate, and it has 4 oxygen. Okay. Now, they work kind of like exponents, like parentheses would, right? So, like, there's 1 barium, but here there's 2 of these things, but these things consist of 1 nitrogen and 3 oxygen. So that's really saying 2 nitrogens and 6 oxygens, right? So, I mean, subscripts they use in chemistry, but think of them like exponents if you're a math person. It behaves the same way. Then over here, this molecule has 3 bariums. It has 2 of these things, but those things each consist of a phosphate and 4 oxygen. Or there are really 2 phosphates and 8 oxygen. Over here, this is 1 sodium, 1 nitrogen, 3 oxygens. Okay. But in order to make this balance, we need these things. Everything's got to maintain, right? You can't lose stuff. You can't gain stuff, right? Everything's got to. So basically, individual element wise, all the sodium's got to maintain. All the phosphorus has got to remain. The barium, the nitrogen, the oxygen, they all have to remain the same. The only thing that you can change here is how many of each one of these. So that means there would have to be some number out front of these. Okay. So many of these molecules of this sodium phosphate plus so many molecules of this barium nitrate would turn into so many molecules of this barium phosphate and so many molecules of this sodium nitrate. Okay. So basically, what we got to figure out is how many of each one of these 4 molecules would need to be there so that everything balances. Okay. One way you could do this, and that's probably the way you learned, is you could just literally guess and check until you find the ones that work, which is fine. Okay. But we can use this a little more mathematical, especially this system of equations. We got a bunch of unknowns, so this is screaming system of equations. Okay. But how you can do it is almost you can do it more like a vector. Okay. And by the vector, what I mean by that is you can think of this is a vector, this is a vector, and it's going to turn into this is a vector, and this is a vector. Each vector would consist of a bunch of different molecules. And so the molecule, or not the molecules, but each of the individual elements. The elements would be the different elements within the vector. So what I mean by that is, okay, so think of it as you got a bunch of overall, we got a bunch of sodiums, there's a bunch of potassium, there's a bunch of oxygens, there's a bunch of bariums, right? There's a bunch of nitrogen, and I think that's it, individual wise, right? You got Na. Oh no, then there's regular. No, that's it. So we got Na, the phosphorus, oxygen, barium, and nitrogen. Okay, so 1, 2, 3, 4, 5. There's 5 different elements floating around. So basically, what I'm saying here is we can set up a vector for the first one plus a vector for the second one, and that should turn into a vector for the first molecule on the second side plus so many of these, right? So this first molecule, it has 3 sodiums. It has 1 phosphorus. It has 4 oxygens. It does not have any barium. It does not have any nitrogen. The second molecule has 1 barium, 2 nitrogens, and 6 oxygens. It does not have any sodium and it does not have any phosphorus. Okay. Over here, this one's got 1 barium, no, 3 bariums, 2 phosphorus, 8 oxygens, no sodium, no nitrogen. And the last one here has 1 sodium, 1 nitrogen, and 3 oxygens. No phosphorus, no barium. Right? And the whole point of what we're trying to get to is so many of these, plus so many of these, plus so many of these, plus so many of these, or I should say, so many of these plus so many of these should equal so many of these plus so many of these. Right? There's your vector equation. Okay. So, how do I solve this vector equation? Well, I could think of it just like we were doing the other one. I can move everybody to one side and then try to get it to be a homogeneous deal, right? And just, okay, so we're not here all day with this. How do I solve a vector equation? We can set up a corresponding matrix, right? So the matrix is going to be 3, 0. Now, this is going to come over here. So really, it's going to be 0, then -1, right? This is going to be 1, 0, -2. Oh, what am I doing? I cannot count. 1, 2, 3, 4. There we go. But you're going to have 1, 0. Move this over is going to be -2. Move this over is going to be 0. Okay. There's going to be 4 of these, 6 of these. Move this over is going to be -8. Move this over is going to be -3. Right. 0, 1. Move this over is -3. Move this over is still 0. Then 0, 2, 0, -1. Okay. Right. So basically, it's the 31400000612. Then these are moving the other side. So it's 0, -2, -8, -3, 0, -1, 0, -3, 0, -1. Okay. But if I move everybody over here, then what's left over here is technically the 0 vector, right? So this again is a homogeneous system. Okay, so again, this will always have a solution. It's either the really boring, trivial one, meaning this will never balance, right? I mean, you always be 0, right? I'd have to have 0 of these plus 0 of these. Again, boring. So what does that mean? There's probably going to be an infinite number of ways to make this work. Okay. Okay. So then usual stuff from then here, you can use calculators. So then let's do the matrix here. This is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? So 5 by 5. So 3, 0, 0, -1, 0, 1, 0, -2, 0, 4, 6, -8, 3, 0, 0, 1, -3, 0, 0, 0, 2, 0, -0. Okay. Let's just check. All right, so we got 31460000612, 0, -2, -8, -3, -1, 0, -3, 0, -1, and then all zeros. Right on. All right. So if we row reduce that, it turns out again we got some nice fractions here, right? So basically, this is going to turn into, let's see it. All right, so we got 1, 0, 0, -1/3, 0, 0, 1, 0, -1/2, 0, 0, 0, 1, -1/6, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. All right. All right. So what does that mean? Pivot column, pivot column, pivot column, non-pivot column. So that means everybody depends on this X4, right? So the dependency is here on this X4. If I know what X4 is, you really know what the rest are, right? Or basically, I can set up my solution vector is some multiple of X4, where X1 would need 1/3 of it, X2 would need a half of it, X3 would need a sixth of it, and then X4 clearly needs itself, right? So technically, there would be the solution. Okay. Now here's the thing. Hold on. Wait a minute. Okay. What did we just do here? This would be all of the solutions to this vector equation. Okay. There's infinitely many of them. But as far as the application here, you can't have fractions, right? I can't have part of a molecule. I can't have part, right? There's either one of these, two of these, three of these, four of these, right? These have to be whole number, right? Nor can they be negative, right? I mean, like x sub 4 could clearly be a negative number here. To solve this equation, this could be a negative number. It's just that all 4 of them would be negative. The math behind this vector equation would work perfectly fine, okay? Negative number of molecules doesn't make sense for its application, okay? So, I mean, like, I guess I'm saying is vector equation wise, whole lot of solutions. But as far as the chemical equations, you need your variables to be whole numbers. Okay. Oh my God. So in order for them to be whole numbers, basically I would need all of these. So how could all of these end up being whole numbers? So that means x of 4 would have to take on a value that would make all of these not be crazy fractions anymore. So you would need a common denominator, right? 6, 2, 3, the common denominator would be 4. So what that means is that x of 4 would have to be a multiple. Guess we've done this notation. So K, that Z, remember real numbers, it's like an R, but this is the lazy way of saying integer. So if K is an integer, x of 4 would have to be a multiple of 6, right? So what, for example, if K were 6, or well, if K were 1, technically, then x of 4 would be 6. Then this would be 1, this would be 3, this would be 2, right? If K were 2, then this would have been 12, right? Then this would have been 2, then this would have been 6, then this would have been 4, right? If K were 3, then this would have been 18, this would have been 3, this would have been 9, then this would have been 6, right? Oh, sorry, you can't see what I'm doing there. Sorry. Right? If K was 1, I'm using basically 6 for this. But then multiply this by 6, multiply this by 6, multiply by 6. That's what you're getting here. If K is 2, basically it's got to be nice multiples of 6 to guarantee these are nice whole numbers. So if K is 2, this would have been 12. 12 divided by 6, 12 divided by 2, 12 divided by 3. If K is 3, then this would have been 18. 18 divided by 6, 18 divided by 2, 18 divided by 3. And then the point is this list would keep going, right? So there are technically infinitely many ways to do this, but they would have to meet this format. This has got to be a multiple of 6. Then you could figure out what the rest are. And then you would have a truly balanced chemical equation, right? So keep that separate. Factor equation has all kinds of answers. The whole number part, in order for the application, there's only some of them that, right? Again, there's all kinds of crazy applications you can do here, but one other type that we're going to talk about here is this. It's kind of like a network flow, right? So you could use this in like civil engineering, or you can even use it in like, you can think of it as computer process networking as well. But whatever, the point here is you have different nodes, they call them, or you can think of it as like intersections, right? So there's intersection A, there's intersection B, and there's intersection C. So these, you can think of these are connections or roads, right? So the freeway network. So think of it as there are 80 cars per minute coming in here. And out of this intersection, there's an unknown, right? But these cars are flowing to A, these cars are flowing to B. Then there's a bunch of cars flowing out of this way, and then there's a bunch of cars going this way to A, and there's 20 coming back out of A, right? So basically, what we want to do, two different things here, but the first one here, let's do this. I want to find the general traffic pattern. Okay. So basically, what's going to make this network work? Okay. So basically, you can think of it as each one of these nodes is there's something going on, right? Or each intersection. So A's got its own thing, B's got its own thing, and C's got its own thing. All right. So basically, what's got to happen? A is going to have a bunch of stuff flowing in, and it's going to have a bunch of stuff flowing out. Whatever's coming in is got to be equal to the stuff flowing out. Okay. So what's coming into A? Well, X1 is coming in. X3 is also coming in. So that means those two added together would be all of the inputs going into A, but the output, it can only allow 20 out. And then do the same thing for B. B has got X2 coming in, but it's got X3 and X4 going out. C has got 80 in, but it's got X1 and X2 going out. So basically, we have three equations with four variables, which right off the bat, you hopefully you could say, hey, if I got four variables and only three equations, that means you have an underdetermined system. If you got an underdetermined, they can't all be pivots. So there's no way that you're going to end up with a unique solution here, right? So there's either no solution, the system wouldn't work at all, right? You'd be gridlock, or there's going to be an infinite number of ways to do it. Okay. So basically, it's hopefully you can kind of see. I want to move everything to one side, but wait, this one's slightly different, right? Because remember the other ones, you were talking about, like, go back to the first one there. There was no actual constants. Everything it has a variable attached to it. Same thing with the other one with the chemical. Everything had a variable attached to it. But this one does have some constants. Okay. So maybe here, let's rewrite it like this. Maybe you want to think of this as like x1, there is no x2, then there's an x3, there is no x4, but I want that to equal 20, right? This one, there is no x1, this one's got an x2, but if I move the x3 over, it's now going to be minus x3. Move the x4 over, it's going to be minus x4 equals 0 because I moved everybody over. Now this one, I mean, take the whole equation and flip it, right? So you're going to have x1 plus x2, no x3 and x4, but that would equal 80. Now you can see your x1s, x2s, x3s, x4s constant, right? So this particular one is a non-homogeneous system because you do indeed have a constant here, right? Okay. But it's basically the same. You set up a matrix, right? So it's going to be 1, 0, 1, 0, 20, right? 0, 1, -1, -1, 0, 1, 1, 0, 0, 80, right? But if you didn't see what I was talking about yet, hopefully you can see, like, okay, so if I set it up like this, you can see there's at most you're going to have 3 pivots. There's no way to get to 4 pivots, right? So if there's no way to get to 4 pivots, there's no way you're going to end up with a unique solution. Okay. Now, just the way this is set up already, there's clearly already 2 pivots. So what does that mean? That means either this one's going to be a pivot, and then you'd have a free variable here, or this one's going to be a pivot, and then this one's going to be your free variable. Or none of these would be pivots and you would have no solution. Okay. Well, what is it? Let's check it out. So this would be a 3 by 5. You got 1, 0, 1, 0, 20, 0, 1, -1, -1, 0, 1, 1, 0, 0, 80. All right. So let's check. 1, 0, 1, 0, 1, 0, 1, 1, 1, -1, 0, 0, -1, 0, and 20, 0, 80. Right up. Okay. So let us row reduce that. All right. So sure enough, you can see there's a pivot here, pivot here, pivot here. So that third one is actually going to end up being your free variable now, right? So this is going to row reduce to 1, 0, 1, 0, 20, 0, 1, -1, 0, 60, and then 0, 0, 0, 1, 60. All right. So what does this mean? Now, I don't know, maybe you could jump right to the vector equation of the solution if you wanted to, but since there's a constant now, you're going to have 2 pieces, right? You're going to have a constant vector and you're going to have the free variable part, right? Or hopefully you can see kind of what we were doing before. If that were all zeros, you're going to have the homogeneous part, which has got the variable attached to it, and then you're going to have the constant part to adjust, okay? If you could jump to it, great, but let me write it out just so you see just yet. So remember, what this is saying is x1 would really be minus x3 plus 20. And then x2 would be x3 plus 60. X3 is your free variable. And then x4 just happens to be 60, right? It doesn't have a free variable attached, or it doesn't have a x3 attached to it, right? So your general solution here, right, your x vector, you can think of it as there's the constant part plus the variable part, right? This would have been the solution of the homogeneous part, and this is adjusting for it since it's got a constant, right? So x1's got a constant of 20, x2's got a constant of 60, x3 is a free variable, so it's got nothing there, and then x4 is exactly 60, okay? Now x1 needs -1 of x3, it needs, x2 needs 1 of x3, and x3 clearly needs itself, and x4 does not need any of x3. All right, so there would be your general solution in vector form. Okay. Now, I didn't specify, it doesn't matter, but either way would be fine. But it's kind of nice just to see how that interrelates. Okay. But the point here ultimately is if I know what x3 is, you know what everybody is. Okay. So x3 is the one that matters the most, right? So x3, if I know what's flowing on x3, I can tell what everybody else is doing. Okay. It's also, it's worth noting here, like being able to use this. Okay. So what is the largest possible value of x3? Man, this would be great if we were in class. You could tell me what the largest possible value of x3 is. I mean, if you just went back to the picture and you probably could figure it out, okay? But keep in mind what these things represent, right? These x values are talking about how many cars are flowing on this, road per minute, okay? So these numbers can't be negative, right? I mean, otherwise you got people going in reverse. I don't even know what that would mean. That's gibberish, basically. You can't have negative numbers, right? So, what is the largest possible value that x3 could be? Well, the key to that one would be realizing what x1 is doing, right? Because think about that, right? If x3 were anything bigger than 20, then this would be a negative number larger than 20. And when I add 20, whoops, you'd have a negative number, right? I mean, like here, it doesn't matter. X3 can be as big as he wants. If I add 60 to it, it's just going to get bigger. All good. But here, that's a problem, right? Because as soon as x3 gets bigger than 20, this is going to end up being a negative number. So basically, here, x3 has to be less than, well, I guess less than or equal to 20. That would be the largest value because otherwise, x1, well, basically, if this happens, then x1 would maintain positive. That's the point. Okay. Or think about what that's saying, basically. Right. If there were more than 20 cars going on to here, right? I mean, there's only 20 cars coming out of here, right? So there's only 20 cars coming out of here, and this were more than that, where would they go? Right? I mean, so definitely X1's got a problem, right? If there are more than 20 cars in here, only 20 cars are allowed out, then X1 has got a huge problem, right? Again, if you just look at the picture, you can see it, but you can also see it from the system, right? That's basically it. I mean, like, let's just take the wording and set up whether it's a vector equation, make a bunch of systems, but ultimately it's the same, set up an augmented matrix and then think about what it's saying.